Okay, good morning, Astronomy 1010. How are we doing today?
Pretty good. How are you?
I'm okay. I want you guys to know that Joel got in touch with me this morning, and he convinced me that we should not do a homework today. And I had no choice but to capitulate to his demands. So thanks to Joel, today we will probably just have a little lecture, and then we'll be on our gobbly-turkly going way, okay? Whatever the hell that means. So thanks for joining me here the day before Thanksgiving, although I know it's going to be a weird one, all things considered. Yeah, thank you, Joel.
Hey, I was just trying to be nice to you, Brendan. You got to
know,
be nice to yourself every once in a while.
I know. Actually, so I've kind of got a project hanging over my head, so it couldn't have come at a better time. So good idea. Hey, there's Yin. What's up? She's driving in the car. We could see you. How you doing? Taking the show on the road, huh? I like it. Guys, today we're talking about planetary atmospheres. We may not be doing a homework yet, but we'll do a homework on atmospheres next week. And it's kind of a big subject. There's a lot to learn. So let's see if we can't get into it here. Last time we learned about the layers of Earth's atmosphere. Do you guys remember that stuff? What if we broke Earth's atmosphere down into layers? What would we have?
You would have an exosphere, a thermosphere, a stratosphere, and a troposphere.
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 It may have been hard to read on the board. T-R-O-P, troposphere. And which layer do you live under?
Tropo.
Tropo. Excellent. We also learned that these layers are heated by different parts of the solar radiation, although in the case of the troposphere, it's even a little more nuanced than that. You'll remember this is a picture from the book that nobody reads, okay? Your book. And you can at least download my slideshow and take a peek at it if that works better for you. Slide 25 is a great graphic because it shows you what I referred to as the temperature scale height, the change in temperature in degrees Celsius as we travel through our atmosphere. And it shows you the different wavelengths of radiation that are heating up each of these layers. Sorry, let's clear that out. That was a bad drawing. The troposphere is actually heated from below by infrared radiation coming from the ground. The other layers are heated by ultraviolet. They're heated by X-rays in the thermosphere. And the upper layer, the exosphere, is sort of heated by solar wind. And we'd like to talk about each of these layers in turn. We kind of have to get into some technical deets here today. So I'm trying to decide, I was going to do the troposphere first, but let's start with the exosphere. Let's try to get that out of the way because there's an important formula here today, and it has to do with the ideal gas. So let me stop the share. Let me get out an animation. Sorry, bear with me here. We want the astronomy folder, the S drive, and we want the physics Java apps. And we want to just look at some gas properties once again. When we look at particles in an ideal gas, it's obvious that they're not all moving at the same speed. It may be a little bit difficult to see here, but once the gas thermalizes, once it comes to a uniform temperature, you'll notice that some particles are moving slow and some particles are moving fast as they collide with each other. Temperature measures the average kinetic energy. It does not measure the individual kinetic energies. The particle's kinetic energies changes, but the collective kinetic energy of the box remains constant. In the case of the Earth, the gas is not in a box, but it's bound by gravity, and I showed you guys this last time. I applied some gravity, I opened up the box, and you could see that there was sort of different layers of the ideal gas here in the box. There's a kind of thicker layer that's like the troposphere down below. And then there's this top layer up here that's kind of like the exosphere, where particles are occasionally popping off into space. Only in the exosphere can particles leave and get off into space, because the particles that are buried down below in the troposphere, they're colliding with their neighbors too many times. They're sort of trapped inside the mosh pit. They can't get out of the pit. Only at the exosphere can particles potentially fly off into space if they are traveling fast enough. Hey, guys, I'm sorry to interrupt us so quickly. Can you give me about 3 minutes? I need a little 3-minute pause. Can you just give me one? I'll be right back. Okay. Before I so rudely left you, we were talking about the exosphere and how particles escape into space. Why is that important? Well, because planets lose their atmospheres over time. If you go to Mars today, the atmosphere is so thin that you can't even support liquid water if you wanted to. Mars should be colder than Earth, right? It's farther from the sun after all. I think the average temperature on Mars is negative 50 degrees Celsius. That's pretty rough. If you took a cup of water to Mars, if I took this delicious cup of coffee to Mars and I exposed it to the Martian atmosphere, it would boil. The water would boil at negative 50 degrees Celsius. How is that possible? How is it that water could boil at negative 50 degrees Celsius? Yin, I'm enjoying that you're sharing your top knot with us today. I always like it when more humans join the class. How could water boil at negative 50 degrees Celsius? Is that scientifically possible?
No,
Yes.
Yeah.
Why?
because it's cold and it's in the negatives.
Hot makes things boil, right? You turn the heat on you turn the gas flame on your stove when you want to boil water for tea. No one could imagine how water could boil at negative 50 degrees Celsius. Okay, hold on, guys. It's about
It'd be
pressure.
cold. It'd be like ice.
No, it depends upon pressure, Andrew. Remember, there's this
All right.
there's this concept. This is what's called a phase diagram for water, but every substance has one. It shows you whether or not your material, like water, will be a solid, a liquid, or a gas at various temperatures. You are incorrectly assuming, because you've lived your entire life basically at 100 kilopascals here in the ocean state, you're assuming that water is always going to freeze at 0 degrees Celsius, and you're assuming that water is always going to boil at 100 degrees Celsius, because that's the pressure of our atmosphere, 1 bar.
That's all
On
fine.
Mars, the pressure is like 100th or less of the pressure of Earth's. There's so little gas there that water can actually boil somewhere near negative 50 degrees Celsius. Right?
Well, water boils at a lower temperature, like in Colorado, even at like 6,000 feet.
Right. So that's a good point, because we're here at the ocean state, so we're pretty close to sea level pressure. But if you're up in Colorado, you actually might notice a very tiny change in the boiling point. Definitely the recipes for cooking things changes a bit. I know that from living in Arizona. The time it would take even to kind of hard boil an egg was different in Arizona than it is in Rhode Island. And you can notice that as a person. And those are just very slight changes in pressure from elevation changes on Earth. Mars is a very extreme form of that, where water can boil at very cold temperatures. So one of the reasons that happens, Mars has such a low pressure, because its atmosphere has thinned out over time. And we want to talk about the process that leads to such a thinner atmosphere. What do you need to get off the gravity of a planet? Well, let's remember a good old-fashioned friend of ours called the escape velocity. The escape velocity is a formula that tells you how fast you need to be going to leave the planet. And it kind of applies for gas particles as well as for rocket ships, right? Here's a gas particle. It's located some height in the atmosphere, which we'll call h. And the radius of the planet is usually r. The mass of the planet is m. And because later on we're going to need to consider the mass of the gas particle, we'll use little m for the gas particle. So this could be a hydrogen atom, it could be a helium atom, it could be an oxygen atom, whatever you like. It could even be a molecule, okay? We know that our particle in the exosphere, which is maybe 300, 200, 300 kilometers above the surface, it can escape into space if it reaches this critical velocity. The square root of 2 times big G times the mass of the planet divided by the radius of the planet plus the height in the atmosphere that your gas particle is. If it's close to the ground, H doesn't matter. But remember, to give you examples from Earth, the radius of Earth could be 6,400 kilometers. And if our exosphere extends up to 400 kilometers, that's not something that you want to neglect. You want to add that 400 in to get to your second significant figure of precision. So that would be an example. Of course, you can't actually put them in kilometers. Do you guys remember the units for this formula?
Meters.
Yeah, it's an MKS formula because you've got big G. So this has to be in meters. This will be important for your test because you're going to have to do this for your test. And this will be in kilograms. Now, this might be too much to ask, but at some point when I introduced this formula, I had us calculate the escape velocity of Earth from the surface. Do you guys remember what that number was in kilometers per second? Close to 11 kilometers per second. Okay. Anyways.
Technically, it's I remember technically from the summer session, but
yeah, it's a teensy bit less than that. Okay. This tells you that a particle that travels at a, so typically for Earth, it might be around, let's put this over here. Let's remind ourselves that for Earth, the escape velocity is usually around 11 kilometers per second. Something around that. That tells me that a gas particle can only escape Earth's gravity if it travels at 11 kilometers per second. But there's just one awkward thing about that. Let's look at our model of an ideal gas again. Oh wow, some gas particles have boiled away. Let's add some light species, shall we? Cool, now you can see some particles kind of jumping out. Not every particle is traveling at the same speed. Some particles are traveling slow, some are traveling fast, and some are traveling in the middle. Do you guys think that there's equal numbers of particles traveling slow, medium, and fast? Or should there be some that are, how do you think that's distributed, right? Do you think it should be equally partitioned between slow, medium, and fast particles? Are there more fast particles? Are there more slow particles? Is it like a bell curve where there's more medium speed particles? What would you guess? If you had to guess for fun.
probably
How does nature
bell
do it?
curve.
You think it'd be a bell curve?
Probably.
It's kind of like a bell curve, Joel, but it's different, okay? It's its own unique distribution. Now I got to talk to you about something that's a little techie here, a little bit over your pay grade, but we're going to do this, okay? So follow along. I'd like to introduce a concept, and let me pose it in the form of a question so you can understand what we're doing here. The question that we're trying to ask is this: how many particles in the atmosphere, or in, let's say, the exosphere, or in any gas, are traveling sort of slow, oops, dyslexia, are traveling slow versus medium versus fast in terms of their velocity, okay? The answer is a unique distribution in nature that gas particles obey, known as the Maxwell Boltzmann distribution of speeds, or sometimes just the Maxwell-Boltzmann distribution. This is something you'd spend a lot of time studying if you were a physics student, okay? We're going to represent it as a little graph here so that you guys can understand what's going on. The graph is kind of like a histogram, kind of like if you plotted grades of students or the height of students in this classroom. In a histogram, we plot the number of particles. This is the number of particles on the y-axis. And on the x-axis, we're going to plot the speed in, say, kilometers per second. So this is your velocity in kilometers per second, where a particle's speed can go anywhere from 0 kilometers per second all the way up to, well, probably infinity, but I'm probably going to cap it off close to the escape velocity of Earth. Because what I'm trying to do is I'm trying to figure out, are there any particles that are actually traveling fast enough to get into outer space? Let's have a thought question before we proceed here. What would the distribution look like if all the particles, if they were equally partitioned into slow, medium, and fast speeds? Could you tell me what that graph would look like? Let me ask that question again, because did you hear the question? The question is, what would your distribution look like if you had equal numbers of particles traveling at slow, medium, and fast speeds? What would the graph look like?
It'd be a straight line.
That's right. It would look like this, right? Because you'd have the same number of particles moving at every velocity you could imagine. Now, a bell curve, which is called the normal distribution or the Gaussian distribution, would mean that there were sort of a few particles traveling fast, a few particles traveling slow, and most particles had some medium speed. That was Joel's prediction, which is actually pretty close to the truth. The real velocity distribution is a unique function that nature has invented for gases. I don't know why nature does it this way, but she does. And the graph called the Maxwell-Boltzmann distribution of speeds looks like a bell curve at first, but it legendarily has something called a high-speed tail with a few more particles moving fast than slow. So this is your high-speed tail. I'm telling you guys, the gases, the air that you're breathing right now, all of those particles are bouncing around according to a Maxwell-Boltzmann distribution of speeds. And what does this mean? This means in this red zone here, any gas particles occupying the high-speed tail in excess of the escape velocity, these particles can escape the gravity of your planet. And that suggests that there's always some particles that are leaking into outer space. Atmospheres are a leaky ship, okay? They leak into space. One way we parameterize the Maxwell distribution of speeds is we say, okay, this is getting too confusing. I'm not even sure what you're talking about anymore, Brendan. Could we talk about the average speed of the gas particles? That would be like the most probable speed, and we have a name for it. It's called the thermal speed. It's not that all the gas particles are traveling at the thermal speed. It's just that the most particles are traveling at the thermal speed, so it becomes kind of a representative of your gas. If an atmosphere gets too hot, the thermal speed will go up. If the atmosphere is too cold, the thermal speed will go down. There's an equation for it, obviously. It's one of your two new equations this chapter. Hang on to your socks, okay? I love this picture, but I don't want to erase it. I'm going to go up. That's what I'm going to do. Introducing a new formula that we need for homework, I guess, next week, now that I canceled today's homework. It is known as the thermal speed. The thermal speed tells you that the velocity of your gas particles in meters per second is most likely to be the square root of 2 times K times the temperature divided by little m, which is the mass of your particle. So this is the particle or molecule mass, obviously in kilograms. This is an MKS formula. T is the bloody temperature in Kelvin. Do you guys remember what little k is? Probably not, but what's K? It appeared in the ideal gas law as well.
The Boltzmann constant.
Hey, Noah. Nicely done, sir. You got a future in science. The Boltzmann constant is a constant of nature that shows up anytime gas particles are involved. It's in the ideal gas law. And I don't have a place to write it down, so I'm just going to write the value quickly. It's 1.4 times 10 to the minus 23rd joules per Kelvin. Luckily, Noah, although that number is annoying, it stays the same, so we never have to do anything else with it. That'll be right on your equation sheet, by the way. By the way, I should, at some point, could you remind me next class that I should give you the second formula sheet so you can start training with it? The second formula sheet's like the first, but it has more formulas, and that's what you'll need for your final exam. Okay. Why don't we try, let me show you a Maxwell distribution function for gas particles in Earth's atmosphere, because this is kind of technical stuff, so I kind of have to like give you a few examples. Do you guys remember the composition of Earth's atmosphere from last class? What is Earth's atmosphere mostly made out of?
CO2.
False. That would mean you're breathing CO2.
Nitrogen.
Nitrogen and
Oxygen.
oxygen. That's right. Nitrogen and oxygen. Okay. This is a Maxwell-Boltzmann distribution for diatomic oxygen at 300 Kelvin. Notice that you can see the bell curve with the high-speed tail. It's the Maxwell-Boltzmann distribution. It looks to me that the cutoff for the escape velocity, I'm going to use lime green here. Hold on a second. That's actually 1 kilometer per second. So the actual cutoff is way the heck up here, okay? Listen, your thermal speed is never going to be the same as your escape velocity. It's almost always going to be lower than that. But the problem is, as the thermal speed creeps closer and closer to the escape velocity, more and more particles will start to leak into space. So normally, we have to apply a test for atmospheric loss. Because think about it. Let's say your gases have a bell curve, that, or sorry, a Maxwell-Boltzmann curve that looks like this. If all of those gas particles jump off the planet and leak away into space, now your distribution of velocities look like this. It goes up to the escape velocity and then it drops down. Are gas particles going to remain that way? No, they are going to thermalize and collide with each other, and they are going to redistribute themselves according to another Maxwell-Boltzmann. This one with a slightly lower area and a new high-speed tail. And then guess what happens? Those particles jump off the planet and escape. And each time you keep kicking particles. In fact, you guys can see that. If you look at my animation, you can see that process at work. Do you see now how there's way fewer particles than there were before? That's because they've been leaking. Let's try it again. Pump, pump. Let's pump a lot of light particles there. Can you see those few particles that are boiling away there, jumping off into outer space? Over time, this atmosphere, as it is, this model of planetary atmosphere, it will suffer some thermal escape, and it will eventually whittle its way down until it's just as thin as the atmosphere as Mars. Why doesn't Earth just boil away its atmosphere? Earth's been sitting around. It's a cookie that's been sitting on the windowsill for 5 billion years, right? It's amazing we have any gas particles at all left, except, oh, wait a minute, I forgot about something. Atmospheres have sources and losses. Mostly, the reason why Earth doesn't lose its atmosphere is because it's continuously outgassing. And there's a few gas particles released through evaporation or sublimation. Hey, students, what's the difference between evaporation and sublimation? Can anyone define these things?
Evaporation goes up in the air, but it boils water, and that one's caused by like erosion and
No.
like
Hold on. When you say up in the air, it's about phase. It's about what phase the matter is in, Andrew. It doesn't matter if it's up in the
it's
air.
in water particles. That's just smoke.
Vapor, right? But so for liquid, evaporation means liquid to gas. Anyone want to try sublimation?
Isn't it from a solid to a gas?
That's right. And so if you need a good example of that, oops, sorry. I like to think of CO2 at room temperature as being a great example of sublimation. If you've ever got to play with dry ice, made some dry ice cream, let's just look at a picture here. Oh, whoa. Okay, so here, let's try dry ice. You know, like fog machines, right? So here you can see a bucket of CO2 frozen, and it's sublimating. It's going directly from the ice phase, frozen phase, into a gaseous phase. In any case, mostly it's just volcanism. I got a little distracted with the CO2 thing. Atmospheres can be lost in a variety of ways. Right now, we are here analyzing a process called thermal escape. That's where the gas particles are just happen to be traveling too fast, and a few of them over time can boil away. The solar wind can exacerbate this. You can also have condensation, which is when you go from gas to liquid, or in the outer solar system, you can have deposition, deposits. That's where you go from gas to solid. Deposition is the opposite of sublimation. You know, on Mars lost a lot of its atmospheric gas through chemical reactions with the surface. Remember that the entire surface of Mars is red. And it's going to turn out that all of that red surface of Mars is basically rust from Mars's primordial oxygen that got bounced off of water molecules. The idea being that on Mars, any early H2O got sizzled apart by solar wind ions, and the hydrogens boiled away, and the oxygens basically went down to the surface and rusted the planet red. In a way, when you look at the red surface of Mars, I was looking at Mars last night in the sky. I could see this big red dot. And it's a red dot in our sky because of all the water that Mars lost, which is really funny and ironic. Okay, in order to know if your gases can escape, you kind of have to compare this number to this number to see if they are close to each other. Now pay close attention to this because you're going to need to do this part on the test. Once you calculate your escape velocity and your thermal speed, bear with me, students, we are going to have to apply the test for atmospheric loss. Okay? And the test goes something like this, okay? It goes like, if the thermal speed of your gas particles is greater than or equal to roughly 20%, 1/5 is 20%, of your escape velocity, or actually, let's pose it this way, guys. Is the thermal speed greater than or equal to 1/5 of your escape velocity? If yes, then the atmospheric gas is lost over time. And over time means a geological time scale. Bonus points if you know what a geological time scale is in terms of numbers. If no, then the atmospheric gas will be bound by gravity, and therefore it will remain on your planet. This is a way you can predict whether or not a planet will lose its atmosphere over time. Usually, even though you're losing a few particles, you're replenishing them by volcanism. I'd imagine that if I was a student learning this for the first time, it might be a little overwhelming, and the best way to deal with it is to just try to do a sample problem. And I think the sample problem that we're going to do is the one that I showed you here in the slideshow. We're going to try oxygen, an oxygen molecule in the atmosphere of Earth. Let me know when you have this down so I can proceed. Okay. Andy,
Got
let me,
it.
all right, I'm going to erase now.
Brendan, does it have anything, so with the particles escaping, does it have anything to do with the gravitational pull of the planet?
Yeah.
Or
The more mass the planet has, the better it's able to hug that atmosphere to the ground. So let's try that out. Let's imagine we have an O2 molecule on Earth. Oh, let's not say on. In Earth's exosphere. And let's use our graph to get a reasonable height for the exosphere. So we know that the mass of Earth is 6 times 10 to the 24 kilograms. We know that the radius of Earth is 6,400 kilometers. And let's say the exosphere, I'm going to want to use like 300 or 400 kilometers, but let me just fact check that by going to your slide there. I don't know if it was 12 or what it was. Somewhere around here. Shoot. It looks like the exosphere starts somewhere around 112 kilometers. Let's go out to 300 kilometers, just to imagine one that's really high up there, okay? So the height will be 300 kilometers.
I can't see that. It's blurry.
Is it blurry for everyone else?
yeah,
What? It's crispy clean on mine. Okay. Is that better?
Yeah.
All right. It leaves me a little less to work with, but fine. The mass of an O2 molecule.
it's still blurry.
What? Heva, is it blurry for you? What? What the shit's going on here?
It's only better because you moved it closer.
Right. Okay, so that means
Like
we've
the
got
focus is
my
focus is off. Like you're in focus, just the board's not.
weird. It's
There it goes.
that's not happening to me. Hold
It's
on.
better now.
Let me cut down. It's better now? Guys,
Yeah.
I don't know what that was all about. Maybe
Logitech strikes
why
again.
isn't on my phone? Because that will drag and drain. Nope, my Wi-Fi's
Logitech
off.
struck again.
I don't know what happened, guys, but Ava says it's better. So you all experienced the same thing. So is it okay now?
Yeah, it's good.
Okay.
Yeah.
Do you guys know how many protons are in an oxygen molecule? It's 8, right?
Sure.
Well, oxygen is atomic number 8. The most proper isotope is 8 protons, 8 neutrons, which is 16 times that of a hydrogen atom. But if it's O2, there are 2 molecules. So 16 times 2 is 32, right? It's a molecule of oxygen is 32 times greater than hydrogen. And I always remember that hydrogen has a mass of 1.7 times 10 to the minus 27 kilograms. So let's quickly multiply that. Get out our calci. .4 times 10 to the minus 26 kilograms. That's the mass of my gas particle, little m. Oh, we need a representative temperature from the exosphere. Let's go back to that. Let's go back to that graph again to get a representative temperature. How hot, according to this graph, would you say an oxygen molecule would be at a height of 300 kilometers? I guess the graph probably. Actually, you know what? Let's get the real graph. Fuck this cartoon thing, which is made by weed smoking artists. Let's get the one from a graduate book here. Yeah, there we go. Oh shoot, this doesn't go high enough, does it? Nuts. Well, it's clearly going to be close to 400 Kelvin. All right, let's go back to the cartoon one again. They should have measurements for this. Guys, do you have calculators handy? Can you do me a favor? I want you to convert from Celsius to Kelvin for me. What would 100 degrees Celsius be in Kelvin? 100 plus 273 is 373, right?
Yep.
Let's use 380 Kelvin. I'm kind of making this up, but that's okay. Let's say the temperature of the gas is like 380 Kelvin. Okay. First, what we do is we calculate escape velocity. Now, remember, the escape velocity will be the square root of 2g mass of Earth divided by the radius plus the height in meters. Can you guys help me get r plus h in meters?
6,700 kilometers.
And how many meters would that be?
6.7 times 10 to the 6th.
Very good. So we have 6,700 kilometers. For those of you who want to do it slow and steady, remember it's 1,000 meters per kilometer, which gives what Joel said, 6.7 million. Notice that after 2 semesters with me, Joel can do this stuff in his head just like I can. It's easy peasy pie. You get good at this stuff. Okay, so the escape velocity from Earth then at the exosphere will be the square root of 2. Let's use the actual value of g so we can get a better estimate here. 6.67 times 10 to the minus 11. I'm going to leave the units out. Actually, that's not good for you guys. The units are meters cubed per kilogram per second squared times the mass of Earth, 6 times 10 to the 24 kilograms, all over 6.7 million meters. Okay, guys, this is your job. Punch that up for me, okay? And this is velocity of escape. So we should write ESC on it. Now I'm going to get some ice water. When I come back, I want that number. right, what'd you get? Well, you were punching, right? Yin, I'm sure you were punching really hard, weren't you? Nice. Very nice. Hey, what's up, folks? Road
You
trip.
got something.
Andrew, can you read it to me?
Actually, no, not right now. I need to look at it longer.
Cam, that looks too big. I think you forgot to square root.
Kilometers per second.
Yeah, 10,900, 11. They basically got 11,000. The same thing we expected. 11,000 meters per second, which is 11 kilometers per second, right? That's just a confirmation of what we already knew. I'm going to erase now, guys. It's time to do the thermal speed. Today's lecture is a little techie, okay? There's no way around that. Let me erase. Okay, second order of business, we calculate the thermal speed. This part is new for you guys. So find V therm. That's the second order of business when we do these problems. Okay, the thermal speed that you just learned is the square root of 2 times K times T divided by the mass of the particle. That is the square root of 2 times 1.4 times 10 to the minus 23rd joules per Kelvin times the temperature in Kelvin, which we decided was 380 Kelvin. Shoot, I'm running out of space here, guys. Times 380 Kelvin, all divided by the mass of our particle, 5.4 times 10 to the minus 26 kilograms. Okay, punch them up. Quick like a bunny now. I ain't got all day.
Brendan.
Yep.
Oh, you see it?
Sort of. Could you just read it to me? Like, give me it, round it up for me and stuff.
440.
I have no room.
440 what?
Let's see. K's cross canceled. Joules per kilogram?
Square root of joules per kilogram.
Yeah.
Shoot, Joel, it's time to go to unit jail. What is the square root of joules per kilogram? I don't suppose you remember what a joule is in the MKS system of units, do you? What is a joule
Watts.
energy equivalent to?
Watts.
No. Here's how I do it. Kinetic energy is measured.
Newtons.
No, that's force. Joule is energy. Do you know the formula for escape velocity? I'm sorry. Do you know the formula for kinetic energy? You don't know the form? Who the shit am I talking to here? I thought I was talking to a bunch of enlightened science students. Now I'm just talking to randos.
And kinetic energy, it's like a half times mass times volume squared.
Not volume, velocity. Cam, it's
Velocity.
wrong. Cam, you got the wrong answer. Do I have to do this for the people in the back? Okay, look. First, let's get the number, then let's get the units. Watch me now. Watch and learn. And Yin, you better pay close attention because you want to know what's going to happen, Yin? When you start not being able to do this on the exam, I'm going to be right back at you, okay? That's what I'm going to say when you fail the exam, okay? All right, here we go. 2 times, whoop. All right, here. 2 times 1.4 exp 23 negative times 380 divided by 5.4 exp 26 negative. Then we hit equals, and then we shift. Yes, Cam, now you got it. Square root. So we got 440. Joel is still trying to figure out the units. Noah, good job, Andrew. Noah remembered that the formula for kinetic energy is 1/2 mv squared. So Noah, you should know the units of a joule then, right? What are the units of a joule? Do mass times velocity squared in your head. Sorry, that's radical joules per kilogram.
Kilogram meters per second.
Meters squared per second squared. You have to square the velocity.
Oh, right.
Square distributes to the units. So then you have kilograms, meters squared per second squared over a kilogram, square root of all that. What are your units?
Meters per second.
Yes. The answer is 440 meters per second. How many kilometers per second is that, hot shots?
0.44.
Excellent. That's how fast a typical oxygen atom, or molecule rather, is traveling in our exosphere. Is 0.4 kilometers per second fast or slow? How does that compare to a car speed? Yin's in her car right now, taking a road trip with her buddies. They're probably going to Thanksgiving dinner, spreading COVID around. Okay. I'm just happy you're not a troll today. That's all. I'm tired of the trolls. Let's look at 440 meters per second to miles per hour. Oh, shoot. Not miles per gallon, miles per hour. That's 900 miles per hour. That's how fast particles of gas travel around in our atmosphere. Oh, you're going to the doctors? Okay.
Man, you could get to California in 2 hours going that fast.
Isn't that crazy?
So.
Wait, so let's talk COVID for a second. If I exhale some COVID-infected air, why doesn't it travel to California in 2 hours? Thought question. Why can't it get to California in 2 hours if it's traveling at 900 miles per hour?
You're not breathing that fast, right? I thought that was.
Yeah, that's how fast the particles are traveling. The individual particles of gas are traveling at 900 miles per hour. As Joel points out, you could get to California in 2 hours. So if I cough some COVID-infected air and those molecules are traveling 900 miles per hour, why don't I have to worry about that getting to California in 2 hours?
Is it because the molecules are so small that they have to cover a greater distance?
No, the distance is the same, regardless of the size of the molecule.
You're going to hit other particles on the way?
That's right, Noah. Now Noah understands. The concept is called the mean free path. It's about the bloody mosh pit. And now I lost my stupid animation here. But the gas particles might be traveling wicked, wicked fast, but it doesn't matter if they're traveling fast because they're smashing into their neighbors so many bazillions of times per second, they effectively can't get very far. They're kind of buzzing around in place. I mean, they do eventually wiggle their way around, but they're not going to get to California in 2 hours. By the way, in the exosphere, that's a different story. In the exosphere, the mean free path is large enough where the particles do actually get through the mosh pit. That's why the exosphere is where particles leak into space, okay? Now we have to finish the job. I'm sorry to be like teching you out here before Thanksgiving, but the issue is we're going to be doing this on the test, okay? So now let's apply the condition for atmospheric loss. I'm just going to back this thing up a little bit here. So the question that we're asking is, will O2 be lost to space on Earth? Well, let's apply the test. the thermal speed is 0.44 kilometers per second, which is very much less than 1/5 of the escape velocity. What is 1/5 of 11 kilometers per second?
2.2.
2.2. So what's the results then? What have you learned? Will oxygen be lost to space or will it remain on Earth?
Hell no. It'll remain.
Hell no what?
It'll remain.
Yeah, that's why we haven't gone, that's why we haven't lost our oxygen in 5 billion years. O2 will remain. I assure you that if we had done this for hydrogen gas, that would not be the same. Hydrogen will escape over a geological timescale. Earth is not strong enough to hold on to hydrogen gas. Otherwise, it would be the planet Jupiter. It would have sucked up all the hydrogen and helium out of its local nebula environment when the solar system was forming. And we would have lived on a gas giant or something. Actually, we wouldn't be around. That's the sad truth. Okay, I'm glad we had that talk. You guys now understand the concept, which is known in planetary science as thermal escape. Look to be doing more of those problems before the semester ends. Some legendary experiments in planetary science come from studying thermal escape. All right, let's change tactics a little bit. Let's leave the exosphere. Let's travel down through the thermosphere. Let's travel through the stratosphere, and let's eventually land on Earth. Shoot, didn't somebody do this? Isn't there a guy who jumped out of like a space pod? Wasn't his name Felix Baumgartner? Do you guys know what I'm talking about? About Red Bull Stratos?
Oh
Wanna
yeah,
have
I
some
saw
fun?
that.
All right, so tell me what Red Bull Stratos was about then.
So it was about some guy that jumped from on top of Earth.
Well, he had to take like a little space capsule
Yeah, he
up into the
took like
stratosphere, right?
yeah.
I think he had like a hot air balloon or something.
Yeah,
Oh,
he had this hot air balloon. And let's get a photograph from this here. I just want to share this with you. Here's one. Here's another one. Oh, this is nice. Nice big picture. He jumped from a height, I believe it was 39 kilometers or 40 kilometers up. So that puts him in what layer of our atmosphere?
Exosphere.
Nope.
Stratos.
Yeah, that's why it's called Red Bull Stratos, right? It's not called Red Bull Exos. It's called
Has
Red Bull
anyone
Stratos.
done that?
Well, he has now. He jumped from right up here. That's
No,
about
the Exo.
Oh, no. No. That would be, this was dangerous enough. That would probably be suicide. I'm not exactly sure why, because, oh, no, I know why, because your velocity would keep increasing. As you fell down and you accelerated, your velocity would go up and up and up. That would be a suicide mission. But he already traveled faster than any other human has traveled outside of a space craft. He broke the sound barrier. He went above Mach 1. And here, can I say something? This is only the second layer of Earth's atmosphere, right? The second layer of Earth's atmosphere. And can I show you that picture again, guys? I don't know about what y'all thinking, but that shit looks like outer space to me. That don't look
There's
like,
outer space.
that
That's
don't look
what
like
I
no
thought
layer
was
of Earth's atmosphere. That looks like freaking outer space, right?
it basically was. He said when he jumped, his clothes didn't even ripple when he was falling.
Yeah, that's why he's got that crazy spacesuit on, right? Any of us, if we had been in the stratosphere, we would just think we were in outer space. You can see the curvature of Earth. You can see the nighttime stars. In fact, Noah, if I remember correctly, what I read about it, he had to practice this very delicate little bunny hop because there is so little air friction up there. You're basically in a vacuum that if he got any kind of spin at all, he would remain spinning out of control and all the blood would slosh to one part of his brain. He was going to lose consciousness and die. So they were really worried that if he gave himself too much of a twist, in fact, if you've seen the video, he actually did start to spin out of control and he lost consciousness. And for a few minutes, they thought he had killed himself. And then he regained consciousness when he hit the atmosphere. Honestly, it's so good. Let's just waste a little time here, a little Thanksgiving, you know, goof off. And let's just, we can't watch, the whole thing actually only takes about 15 minutes, but let's watch full point of view. Where is it here? Let's watch just a couple of minutes of it here. Oh, wow. I've actually never seen it from his point of view, but I bet it's pretty crazy because oh my gosh. There's a full one. I've never seen this one
You
before.
have to unmute it.
Wait, am I sharing? Oh my
There we
gosh.
go.
Am I sharing the sound with you guys? Can you hear the sound?
Yeah.
That looks scary AF, as the kids say. At some point he starts to split. Let me show you. Woo! All right, I've got it. Hold on. Note to self, I want to watch that one later. But Red Bull
442
Stratos jump.
kilometers an hour.
This is the one. Oh wow, this is in high definition too. Here, I want to show you guys this moment where he steps out of the capsule, just so you can imagine what a bold thing this is. So here he is, getting out of the space pod. Okay. And I just want to go to the moment where he jumps. I mean, look at that. That's a layer of Earth's atmosphere, guys. People study. Here we go. He mumbles some stuff into his microphone. Not sure what he's doing there. He's getting make sure his parachute's ready to deploy, probably. Whoa. Look at this. There you go. Woo! That's crazy, right? That's so crazy. And now there's very low resolution because you're so far away, but look, you can see him spinning out of control. And at some point he loses consciousness. There he is. 729 miles per hour, right? That's so crazy. These guys are like, well, we just killed this guy. They got a mission control there. And now here's what's interesting from our point of view. When he hits the troposphere, when the gas particle density increases, it provides friction, which slows him down. And then he regained consciousness. They stabilize the spin. And then next thing you know, here he is floating over the Mojave Desert. And what is maybe like 11 or 12 minutes later, here he is landing. Look at this. Oh, you bastard. You bastard. The internet just froze on me. This always happens right here. Here we go. Wow. Can you imagine that? That guy jumped from 39 kilometers, lands on his feet, right? And he was probably one of the few humans who actually got to travel through just two layers of the atmosphere, and to experience that all firsthand. Can you imagine what an awesome, wild adventure that must have been? Anyways, the troposphere has a lot more gas particles than those upper layers. Those upper layers are very thin layers of gas. The troposphere is where the party's at. That's where the gas particles are. And in order for us to understand how tropospheres keep a planet warm, we first have to do a little mind adventure about what makes the air outside hot or cold on any given day. Let's have a discussion about the role that atmospheres play in changing the surface temperature of a planet. So let's ask the question, what affects the surface temperature of a planet? I think I might have actually told you this before, but the answer is 3 things. Can you guys guess what they are? What are the 3 things that determine whether it's warm or cold outside? For a planet. I mean, like just for a planet in general.
Well, the first one's sunlight.
So that would be how close or far you are to the sun then, right, Andrew?
Yes.
Yes, I agree with you. Sunlight is the correct answer, but you get more of it if you're close and less of it if you're far. So that's the first thing, is distance from the sun. And by the way, all of these things are going to appear in the equation that I'm about to give you, D, and we're going to measure it in astronomical units in this equation. What's the second thing? The second thing you might actually have a hard time guessing. It's about the reflectivity of a planet. It's called the albedo. The albedo, which looks like albedo, is the percent reflectivity of your planet. And we're going to give it the symbol A. A is a number that can go from 0 to 1. It's a percentage of reflectivity. So the domain of A is a number that's between 0 and 1. If A is equal to 0, you have a perfectly black planet. It reflects 0% of your light. If A is equal to 1, you have a perfectly white planet, or you might even think of it as a disco ball. A disco ball has an albedo of 1 because it reflects 100% of, well, that's not really true, but let's lie. Can I be honest with you guys? There is no such thing as perfect blackness, and there's no such thing as perfect whiteness. There's always a little bit of absorption and always a little bit of scattering at work. But I'll lie, because lies are easier to digest than the truth, as we all know. Black planet versus a white planet, 0 through 1. The third factor is actually the greenhouse effect. And we're going to subtract that out in just a moment, but the point is, tropospheres are heated from below by the greenhouse effect. And the greenhouse effect is where infrared is absorbed by greenhouse gases. Do you guys remember what examples of greenhouse gases are?
H2O and carbon dioxide and
Those
methane.
Are the big ones, that's right. Oops, can't spell gases today. CO2, H2O, maybe methane. Okay, for a moment, we're just going to focus.
Oh, I can't see the bottom.
Oh, sorry. Let me know when you're all set, Andrew.
I'm all set.
Okay. With your permission, I'm just going to take a moment to focus on 1 and 2. Because the greenhouse effect requires a planetary atmosphere. But not all planets have atmospheres, but they all do have surface temperatures. And first, we just have to ask ourselves, how hot is my rock in space? Oops, let's get rid of that. Sorry, guys. I just want to cut down on my internet bandwidth here. Okay. So let me show you a picture. Here's the cartoon that we're imagining. And I'm going to ask you guys the question, How hot is my airless planet in space? So how hot is the surface of the moon? How hot is Mercury? That will depend upon your distance from the sun and also what percentage of the sunlight that you absorb. Here's a cartoon showing you some various albedos of different substances from your daily life. Notice that grasslands have albedos of 25 to 30%, meaning they scatter. Sorry. So if you're fresh snow, you're reflecting 95% of the sunlight. If you're grassland, you're reflecting about 30% of the sunlight back into space. Blacktop or asphalt could be anywhere from 5 to 10%. That's why it's hotter in cities than in the countryside during the summertime, because you're scattering more of that light back. Sorry, you're absorbing more of the light, heating up your temperature and re-radiating more infrared back up into the atmosphere, okay? Water is an interesting one. Water covers 2/3 the surface of Earth, but water's reflectivity depends a lot upon the angle of the sunlight. During the mornings and the evenings when the sun is low in the sky, the sun might scatter 60% of the light off the surface of the water. That's why our sailor friends, the ones that go sailing in Newport, they've got to wear those polarized sunglasses or they'll get blinding headaches from scattered sunlight. When the sun is high in the sky, it penetrates deeper into the water and most of it actually gets absorbed, only 10% rescattering. Hey class, what color is the moon? Like, no tricks. You look up at the moon at night. What color is it?
White.
White.
White. Well, whiter. Whitish.
That's what it looks like to me. It looks like a white disk. According to this, Joel, what substance on Earth is closest to the albedo of the moon?
Asphalt.
Yeah. Can you help me understand that? This is basically saying the moon is jet black, but I thought the moon was white when I looked at it in the sky. Can someone help me understand that riddle?
That's the percent reflectivity, but could it reflect, or it could absorb different colors, right?
No, no, no. It's not about colors. It is about reflectivity, Noah, if that's what I'm talking to, or I don't know who I was just talking to there, but.
Didn't you say that the moon was covered in like a dust? Does that affect it?
It is, but remember, the moon is also covered in jet black volcanic rock. Let me explain this conundrum. It's kind of like a photography issue. If you were to go to the surface of the moon is jet black. It's very dark. But the problem is you're scattering only 10% of the light off the surface, but that light that you're scattering is very, very bright white sunlight. Like if you take the spectrum of the moon, it's the spectrum of the sun. It's the same. What the hell? I'm in the wrong slideshow here. I want this one. And I want to go to the picture of some astronauts standing on the moon. Hold on, guys. Could you imagine walking around on the surface of the moon at 588? You know, like when you go to the beach on a sunny summer day and it's so incredibly bright out that it's blinding and you can't even open your eyelids and you have to put on sunglasses and hide under the beach umbrella? Think about how bright that sunlight is. Imagine how much crazier that would be on the surface of the moon, where there is no thermosphere, no stratosphere to block ultraviolet radiation. You're getting the full brunt of the sunlight and you're getting all the X-rays and all the ultraviolet rays. It's actually quite dangerous to be out here for a long period of time. And that sunlight is just beating down on the regolith. The regolith is actually jet black, but it looks grayish in these photos because you're seeing the reflected white sunlight. Sure, it's only 10% of the sun, but the sun is freaking bright. So even 10% of the reflected sunlights is going to look like white light from the sun. However, the surface of the moon is very dark. Just wanted to get you to think about that for a second. There is a formula that will tell us how hot the surface of the moon will be, or the surface of any planet will be, based on distance and albedo. It is called the no greenhouse temperature formula. It's the second big piece of work I have to do with you guys today. May I erase here? Any objections? Okay. Okay, introducing a second formula from this chapter that you'll need for your exam called unimaginatively the no greenhouse temperature formula. It tells us that the temperature of the surface of my planet will be a reference temperature of 280 Kelvin times the fourth root of 1 minus the albedo divided by the distance in astronomical units squared. A is the albedo, which can be anywhere from 0 to 1. And D is the distance to your planet from the sun in astronomical units. Let's try a quick example with this, and then I'll put you guys out of your misery here. For example gratia, let's consider the surface of the moon. Can you guys give me some representative values for A and D? What's the albedo of the surface of the moon?
Seven, around about
7 what?
%,
How do I write that as a decimal, Noah?
0.07.
Thank you. That's right, Noah. Good memory. That was right in the middle of the sliding scale there. Noah, what should I use for the distance to the moon?
1 AU.
Yeah, it's about the same as Earth, right? Okay. Let's try plugging that in. The temperature then will be 280 Kelvin times the fourth root of 1 minus 7%, all divided by 1 squared, which is 1. So we're going to just ignore that. This should probably be in parentheses, by the way. I'll show you all how to punch that in, okay? Andrew, let me know when you've got that copied down, and I'll do a demo.
All right.
So let's do this. 1.
Oh, wait. I can't see the rest of it. Thank you. All right. I'm all set.
All right. 1 minus 0.07 equals. Now, normally we would divide that by something squared. Divided by 1 squared equals whatever. Now we got to take our fourth root. Remember that to do that, you go shift arbitrary root 4 equals, and then we multiply by 280 times 280 equals. What'd you get?
Brendan, can you do that again? I'm sorry.
That's fine. 1 minus 0.07. Then I would hit equals. In the event that your distance was not 1, we would do divided by 1 squared equals. You with me so far?
Yep.
Now we're going to do the fourth root. Shift arbitrary root 4 equals. Now we multiply by 280 times 280 equals.
What's the arbitrary root button again? Is that X3?
It's above the X to the Y key. You have to hit shift and then this key right here.
X to the Y.
X to the 1 over Y. The fourth root is the same as raising to the power of 1/4. So it looks like I got 275 Kelvin. Now, I don't know about you guys, but that means something to me. That number is not random.
Hey, Brendan,
Yeah.
where do the AUs go?
Oh, unit-wise? Noah, that's a great question, and I'm going to tell you the answer, but try not to get bored with me for a second. It is possible, Noah, to cook the books so the units can be in any situation you want. Okay, so Noah, where this comes from, since you have some scientific mind to you here, let me just erase this for a second. This comes from taking the inverse square law, right? And connecting it to the Stefan-Boltzmann law times the albedo. You plug in the luminosity of the sun, which is a fixed number, and you rearrange the equation, and you get a big fat mess. You get something like the temperature is equal to the fourth root of 1 minus the albedo times the luminosity divided by 4 pi d squared. But then you realize that you don't want to be plugging in your d in meters all the time, and you don't want to have to plug in the sun every time. So what you do is you plug that in, and you also plug in a conversion factor to kill out the meters and leave behind AU. And then you extract, oh, this is the fourth power. You extract all of that bullshit out. You calculate a reference temperature, basically what would the temperature be for the sun at 1 AU, perfectly absorptive. And that's all hidden in the 280 Kelvin. So you can always fix an equation, and you can always pull it out so that it says 280, and I could have put this with the distance in inches if I cooked it correct. It would just change my reference temperature. Now the problem is, when a student like you knows a little bit too much for your own good, you're going to ask some probing questions like, why are my units in AU? It's magic, okay? That's the answer. Because I'm so good at math, or someone's so good at math, that they made it magic for you. So you don't have to worry about unit balancing. Notice that basically these should all be unitless so that your temperature comes out in Kelvin. Great question. Hope I didn't bore you with the answer, okay? 275 is not a random number. Does anyone know why that means something to me? What would that be in Celsius?
0 degrees Celsius is 273 Kelvin.
So what would this be in Celsius then? Remember, 1 Celsius degree is equal to 1 Kelvin. Differentials, right? Joel, you know that 273 is... What is it?
0 degrees Celsius.
If 273 Kelvin is 0 degrees Celsius, then 275 Kelvin is...
2 Celsius.
Yeah, 2 degrees Celsius. Why do I find that to be so interesting that the surface temperature of the moon is 2 degrees above freezing? Do you know what the Earth probably looked like when it first formed? The Earth didn't form with an atmosphere, did it? It didn't look the way it does today when the Earth first formed. When the Earth first formed, it probably looked a lot less like the Earth and a hell of a lot more like the moon, except it probably looks like the moon with volcanoes. If you've ever seen Star Trek, if you're a big nerd like I am, you can think of like the planet Vulcan or something, like a volcanic planet. Or for the kids, when you play Zelda and you go to the Gorgon territory and there's all those volcanic eruptions everywhere. It probably looked like that. It was probably airless with volcanic eruptions, things like that, right? I think it's very interesting that the surface temperature rock of the moon, or probably a primeval Earth, was 2 degrees above freezing, because that means when all of those volcanoes start outgassing, they're going to produce water, and that water is going to, sorry, I'm looking at the wrong slideshow here. That water is going to potentially condense on planet Earth. right? See, Earth didn't form with oceans, and Earth didn't form with an atmosphere, but Earth did form with volcanoes. And as the volcanoes pump out water, CO2 and sulfur dioxide, that water is now precisely at the right temperature to condense into a liquid on the surface. It's just above the freezing point. In other words, Earth is barely in the Goldilocks zone. Have you ever heard that term before? The Goldilocks zone is the hypothetical distance at which a planet can sustain liquid water from its star. Goldilocks zone. It's different for the sun than it is for other stars, but we believe that our Goldilocks zone stretches somewhere from the distance of Earth to kind of like the distance to Mars. And we care about the Goldilocks zone because this is the, hold on, let me see if I can find a nice graph of the Goldilocks zone. There we go. Well, this is the Goldilocks zone for Kepler or Gliese 581, a different planetary system. Oh, here it is for Earth. Look. The Goldilocks zone on Earth, shown up at the top, goes from right just before Earth right out to Mars. This is the sort of region where a planet could have liquid water depending on its albedo. Venus, you'll notice, is just a little bit on the edge on the inside of the Goldilocks zone. It was a little too hot for fun, okay? We always want to look for life around planets that are in the Goldilocks zone surrounding their star. So this can be done for other planets as well. But it's just fascinating to me that when you calculate the temperature of the moon, that volcanic rock is just warm enough to melt that water, turn it into, melts the ice and turn it into water, right? Of course, there's no pressure on the primeval moon, or on the primeval Earth, there might have been some gases floating around, so there was probably some pressure. All right. I think that concludes our lecture for the day. You've learned a lot, I hope. Let's go back to our gallery view. So remember, class, today you have been, thanks to Joel's exertions, liberated from homework. I'm sure you've got a lot of stuff going on. I kind of planned on having a little pressure release valve around this time of year. There's a lot going on. But I'm glad that you came and hung out with me and listened to my lecture. It's going to be important for your exam. Next week, we'll resume business as usual. Monday, we'll have a lecture followed by a lab. Wednesday, we'll do a lecture and we'll have homework for chapter 10, okay? Okay. Live long and prosper. Enjoy some turkey. If you're eating turkey, don't spread the COVID around. Get takeout, whatever. Ava, that's a good question. I'm not going to be ready for the Jovian lab, Ava, so what I think we're going to do is we're going to build a telescope. So let me show you something, Ava. Do you remember how we skipped over one of our labs, which was lenses and telescopes? That's the lab that we're going to do. It's actually a pretty cool lab. We're going to build a little telescope. So my plan is that on Monday for lab, we're going to go back and we're going to do this one, which we missed. And then we'll have time for one more lab in the following week. The last lab after that will be, I haven't put it up yet, but there's one on rotations of Jupiter. So that's probably why you're confused. No, it's lab 7, right? Lab 7 is lenses and telescopes, Ava, okay?
How many homeworks do we have left then?
I guess 2. We'll do one next week and we'll do one the week after that. And then I think we're here. Actually, that's a great question. Let's map out our semester. Remember, guys, that I provided you with a schedule in your Blackboard, in your syllabus folder. Let's just look at that real quick. So we were actually supposed to do a homework today. I'm being kind of naughty, all right? Here we go. Today is the Thanksgiving. So we were supposed to do, are we ahead? Oh, no, that's.
No, chapter 10.
We were supposed to do chapter 10 this week, okay? And I'm probably going to end up regretting this decision that I'm making. But I already said it, so I can't go back on it. I also have a lot to do. So we were supposed to do 2 more homeworks. We'll probably do this one, nix this one, and then do that one. That's what I'm thinking is gonna happen, okay? And then after these next 2 weeks, I think we're pretty much at exam time, right?
Yes.
So I'll probably have to skip the 9 and 10 combo, which is sad, but whatever. All right. Class, I'll see you on Monday, okay?
Yeah, I'm on
Happy
the
Thanksgiving.
Yeah, happy Thanksgiving to you as well. Be well.